Let's review heating curves. There's one shown. We have the different states of matter and the transitions between the states. Whenever we're within a given state of matter and the temperature is changing by us adding heat or taking heat away, we want to use the delta T form of the equation, which I've circled in blue in the lower right. And we want to use the constant, that is the heat capacity that is specific to that state of matter. If we're making a phase transition, we use the non-delta T form of the equation, which I've shown in the lower right here. I've boxed it in green, and again we want to use the constant that is specific to either solid-liquid phase transition, if that's what we're doing, or the liquid-gas phase transition, if that's what we're doing. Using the constants given, find the enthalpy change when 679 grams of water at 27.4 degrees Celsius are converted into water vapor at 121.2 degrees Celsius. Here are our constants that were given for this problem. We can see here that there are several of them that have the unit joules, and there is one that has the unit kilojoules. Furthermore, some of them have the unit grams, but a couple of them have the unit moles. We're going to need to be very careful when we do our calculation that the m quantity in our equation is the right unit. Is it moles or is it grams? Well, that's going to depend on what unit is in the constant that we're using at that time. So let's show you. Here's a generic heating curve. We know that for water, the freezing point is 0 and the boiling point is 100, which means that we're going to start at 27.4 degrees Celsius, which would be approximately where that green dot is, and we're going to end at 121.2 degrees Celsius, which is where that red dot is. Clearly here we need to start at the green dot and end up at the red dot, so we're going to need 1, 2, 3 calculations. We're not going to use the constant that applies for this solid-liquid transition. In particular, that would be in these numbers in the table on the left, that would be this number here, 333 joules per gram. We're not going to use that because we're not in that portion of the curve. Similarly, we're not going to use the heat capacity for the solid phase, which is right here. 2.077 joules per gram Kelvin. We're not going to use that number, but we are going to use the other three. Let's first heat the liquid. In other words, we need to go from the green dot up to this bend right here. That's going to need the delta T form of the equation. Let's look at the specific heat for the liquid phase. It's given right here, 4.18 joules per gram Kelvin. We want to make sure that our m has the unit gram. There's our specific heat. And the delta T is final, that is the temperature right up here, which is 100, minus 27.4, and that gives us 206 kilojoules. I've gone ahead and changed that into kilojoules. If you actually multiply this out, it comes out in joules, but I've changed it into kilojoules for a reason. You'll see why here. Once we've done that, we now need to add enough heat to boil the liquid. That would be where this diamond is. In other words, we need to go along this horizontal portion of the curve. The equation to do that would be the non-delta T form, and we're going to use the heat of vaporization here. Let's find the heat of vaporization in this table. You can see in the upper left that it's given as 40.61 kilojoules per mole. In the equation down here at the bottom, the m we want in moles, not grams. Sorry, I don't have room to do it on the slide, but I trust that you can convert 679 grams of water into 37.72 moles of water using the molar mass of water of 18. And we do that again so that that unit, moles, will cancel the mole unit that happens to be given to us in the constant. It's going to take 1532 kilojoules of energy to boil that amount of water. And now we then need to heat the gas from 100 to 121.2 degrees Celsius. In other words, we need to go along this final stretch of the heating curve. That is a sloped portion, so we need the delta T form of the curve. The heat capacity of the gas, I'm circling it here on the left side of the screen with my laser pointer, is given as 36.76 joules per mole. Again, the M we've chosen not as grams but as moles so that it cancels the mole unit that's given in the constant. The delta T, T final, is 121.2 for this little portion of the curve. T initial is 100. That comes out to be, if we convert it into kilojoules, about 29.4. The sum of those then is the change in enthalpy.